Suffix trees are a data structure that allow you to do exactly what inverted indices could not do. They allow you to search for any substring, and it can occur anywhere in the string. You don't even have to know which substrings will be searched in advance. There's no restriction. It can be any sequence of characters. And you'll find out if they occur in the text, and if so, where. It turns out on top of that, suffix trees can do a lot more. And well, okay, I'll call them a magic data structure in the following sense. They solve the problem that on first sight seems very, very hard to solve. And with suffix trees, it becomes almost trivial. So I want you to take a second and think about this problem. It's called the longest common substring problem. The input consists of several texts, just a collection of strings. And you're trying to find the longest substring that occurs in all the strings. Now, a substring is just from position I to j. It's a contiguous range. There's also a similar problem about subsequences that would allow to take the first, the fifth, and the 100th position. So you delete an arbitrary number of characters. That's not what we're talking about. So substring is as we had it before. So it's some contiguous range. Is the problem clear? So here's an example of two strings. In general, it can be more than two strings. Who can find the longest common substring in those two strings? Because the second is not too long. Life? Alive, yeah, I think alive. The R doesn't work, but we can find alive here, and we can find alive here. At least locally, we cannot extend the repeat in both directions, so that seems about the best we can do. It was easy in this case because the second string was really small. If you have many strings and they're all fairly large, it's quite unclear how to do this. So that was correct. The question is, can we do this essentially in linear time? So what this means is the size of the first text plus the size of the second and so on. That's the total length of all the texts. That's the best we can do. We need this. Theta of this is already necessary to just read the entire input. So we're asking up to constant factors, can we solve this problem in the same time that it takes you to simply read all those strings once? And it's I don't give you a fair chance to think about this problem, but maybe you want to do this. Suffix trees will provide a solution to this in essentially that time, but it will take us at least today's session, and maybe I won't completely make it today, to understand how that works. And another piece of history, if you like. So this is a quote from a book, but it essentially claims that another person, Donald Knuth, who is a very famous computer scientist, he wrote influential books in theoretical computer science and algorithms, and he also wrote the LaTeX software, if that means something to you. And he's done a lot of other things. We've already seen the name in the string matching chapter. That's the same Knuth that occurred there. So it means something that he originally thought this problem would not be solvable in linear time. And it turned out he was wrong. Didn't happen so often, but in that case, it turned out he didn't anticipate the concept of suffix trees and all the things that you'll see. So maybe that helps you appreciate a little bit what is to follow. I might also say there's also a piece of warning. There's some tough stuff to follow. I'll try to go slowly and show you the nice parts and ignore some of the nastier parts. And also, suffix trees and the algorithms around them have a long history. Initially, around the 1970s, it wasn't known how to do this at all. Then people eventually came up with the concept of the trees. And it took quite a while before people convinced themselves that it's always possible to construct those trees efficiently. I won't show you these algorithms because they're a little intricate and not as elegant, but I'll show you something more modern. I alluded to this yesterday. I'll show you how suffix arrays are constructed in linear time. That's easily doable. You'll manage to understand that, even though it's a little lengthy, but every single step is fine. And from that, you can construct the suffix tree. So you will see an entire complete solution to this problem that a very famous and very clever person thought was not possible to solve. I hope this is enough advertisement for this unit, and I hope you don't suffer too much. So what is a suffix tree, this magic data structure? It is exactly this. It's a trie containing all the suffixes of the text we're looking at. And in all the rest of the unit, when we say a certain text is given, we always append this end of word marker. That was convenience for the tries so that there's no suffix of the text can be the prefix of another suffix. Okay? We'll build a tree that contains all suffixes of the text. So for every starting position, we take from this position onwards the rest of the text, including this end of word marker. Because we have this end of word marker that doesn't occur anywhere else, no prefix of this can be no suffix can be the prefix of another one, because that would align the end of word marker somewhere in the middle with the text, and it doesn't occur there. Okay? And it's the compact version of the trie, because otherwise we'll be out of luck. So how many suffixes are there of a given text? That's a good question for you. I should have put that on Pingo. Would someone like to scream it out? How many suffixes does the text with n characters have? N? N sounds good. If we add this extra character, you could argue whether or not the empty substring is an interesting suffix, but it's actually not, so we'll ignore that one. So we'll have exactly these we have n plus 1 suffixes, nevertheless. We don't include the completely empty one, but the one that only consists of the dollar is a proper suffix, and that includes 0 characters of the text. Then we have the suffix one longer that includes 1 character, and so on, up to n. That's n plus 1 in total. Okay? I don't think we need an example for that, but you'll see it here in the full construction. So I meant not an example listing all the suffixes, but actually I prepared one. So that's, my favorite word for this unit is banana band, because it has lots of repetitions and not a big alphabet. So you'll see a lot of those. In case you like bananas, I'm sorry. So it's a string of length 9 originally. It goes from 0 to 8, and then we add the dollar. Piece 1 of information from that definition is we don't count the dollar in the length of the text. N is the length of the text without the dollar, but then we add it. Here are all the suffixes of this word in the way we want to define it for this unit. And this is the trie. You can build this trie in the same way I've shown you last time. You would start building the standard trie, and then you can contract the unary edges, the paths of unary nodes. And you'll do exactly that in the tutorials next week to practice that a bit. But here I've done the work for you already. And you can check that all of the suffixes are there. They're listed here in some order. And we find the entire word by, for example, following this path. And if you concatenate all the path labels, you'll find the text. So far, so good? So the magic of suffix trees is not the definition. That's actually a fairly natural thing to consider if you played with these kinds of questions a bit. It's convenient to have a trie with all the suffixes, and I'll show you 5 reasons why later. The magic comes into this game in constructing this trie efficiently. If you do it the way Okay, I'll come back to the construction in a minute. There's one more thing to discuss. The trie of the suffixes, like I defined it just in the last section, it has a copy of the strings in the leaves. We can't really afford this copy, and we also don't need it because all the suffixes are positioned, well, they're suffixes of the text. So why bother storing a copy? We can just store the start index of that suffix. All right. And so there's the 0, that's the entire string. There's the 1, that's the anaban, and so on and so forth. All right. That actually belongs to the definition, but it didn't nicely fit into the red box, so I'll put it separate. Also remember, it's a compact trie, and there's 2 versions of a compact trie. This is the one that is, well, suitable for us humans to think about it. And that's the one we will explain. I'll explain the algorithms on. But it really looks like this in the computer, where you have only the first character of each label, and then the internal nodes remember what's the next character they compare if you follow the child edges. All right? But that's just repetition. That's the same as we did for tries. The only difference really is that in the leaves we now store a single number because we know it's a suffix of this text, so the start index is enough to identify it. How can we construct this suffix tree? That's where the magic comes in. We have n+1 suffixes. We could build the suffix tree in the way I described it. First build the standard trie and then compactify it to get the compact trie. And well, instead of writing the strings into the leaves, directly doing the indices, that's the easy part. That's not a problem. But remember, we discussed this last time. The standard trie can be as big as the total number of characters in all the strings added up. Our text only has n characters, but if I add up all my, okay, I should start with banana, ban, dollar, Anna, ban, banana, ban. Okay. And so on. What I get is such a full triangle of characters, which means there's essentially a quadratic number of characters involved. Okay? So being linear in the total number of characters might be fine for some trie applications, but for suffix trees, that's really not good because that's quadratic in n. So we cannot afford building the suffix tree in this time. It's not an interesting data structure then. And the amazing result that took people quite a while to figure out how to do it is that you can construct it in linear time. Again, that's essentially the same as just reading the text. But it turns out to compute this suffix tree, you have to learn a lot more about the structure of this text. Okay, as I said, the algorithms, historically speaking, they were older than what I will show you, but they're more intricate, and we'll essentially ignore this, but I'll show you a way to construct suffix trees in the end. So let's assume we can efficiently build the suffix trees for now, and first look at what we can use them for. So it's my way of first motivating why I want you to go through all this pain. Before you suffer, you should know why you're doing it.